This talk is called I Don't Know What Graph Theory Is, and at this point, I'm too afraid to ask. And the title was actually my motivation to get into this. So a couple years ago is when I got hired on to Spectre Ops, and I understood the basics of Bloodhound, but Andy Robbins has a interview where he talks about uh, sort of the motivation for how that Bloodhound came about, and his friend says that it's sort of like Graph Theory 101. So getting into that, getting into how they make Bloodhound a little bit more efficient, um, the term got thrown around quite a bit, and I just sort of was, I was like, I could either ask or I could present about all the information in front of a bunch of strangers. So I took the latter in terms of just giving myself the challenge to research it and try to have a bit more better understanding. So a bit more about myself. I am currently a defensive security analyst, sort of like a SOC analyst. Build detections and respond to problems. Before this, I was in the military as a Army DCO Bubba, meaning also doing a bit more defensive stuff. I have a couple certifications, got a degree in computer science. And in my free time, photographer, DJ, gamer, and what my mom calls the reason the rum is always gone. A little bit more into the agenda. We're just going to talk at a relatively high level at first what graph theory is, the problem that it's trying to solve, how it is used in math. And don't worry, we're not going to go down that rabbit hole too much because the math part of it is very intense. So we'll take a deep breath before that time comes. We'll stick our toe into the math side of it and then show you how it's used, at least in our world. So what is graph theory? For this one, I picked the definition from Wikipedia because I feel like this one was the most succinct. Granted, Wiki has their own set of problems, but where it's saying it's just the study of graphs, which are mathematical structures used to model a relationship between objects. And one of the things I'd like to point out here is the phrase objects in computer science can mean a lot of things. But in this instance, think of it as an object will just mean like a programmatic instance of something, meaning a person could be the object and some of their components would be like their name, age, and weight. So you'll hear me use the phrase node, vertice, or object interchangeably, but they're all going to go back to an object in the same way that like C++ is an object-oriented language. So why would you use a graph? The general uses for graphs, and I'm going to have to steal like one of the quotes from the military, but one of the things they always tell you to do when giving people like motivation is to visualize, describe, and then something else that I would have to be in uniform to remember. But the visualization is key for creating a shared understanding, specifically when it comes to like dealing with complex problems and trying to find a solid solution. And graphs are a good way to like analyze trends, analyze relationships, and do it in a way where you can have a shared diction between each other. So towards the bottom, you'll see that I have this described as like the relationships can be described as nouns and verbs. So for example, the object in this instance would be Nicholas, and my relationship to the people in the room would be talking, coaching, teaching, mentoring. And then you could extrapolate that into be really whatever type of a relationship you would like. So how is this like actually represented, or in a way where we can try to distill this into its core concepts? This is where the math starts to come in, and creating a little bit of a shared definitions for this part. The vertices, these are going to be an object or a node, an edge, the connection between the nodes, but specifically the relationship between them. I like to think of the node as the node as the noun and the edge as the verb, meaning the noun is the person, place, or thing, and the edge is what that is doing to the other person, other thing. The graph is just a collection of all the relationships. A tree is another graph, but specifically linear, meaning won't get into cycles, but we'll explain that a little bit more. And then the last two are directed and weighted. So these are a little bit more complicated, but this is where we're going to start to learn a little bit more about algorithms. And the first two basic algorithms are breadth first search and depth first search, that for the rest of this talk, we're just going to call BFS and DFS because that's a tongue twister trying to get the full thing out. But the breadth first search, what this is doing is, given a list, it's going to go through layer by layer. And if you think of an actual tree, inverse tree, where it's going to be like 1, 2, 3, 4, 5, 6, 7, 8, it's going to go sequentially through each one, versus the depth first search is going to traverse down all the way of one branch and then go back up a little, down a little bit more, up a little bit more, down a little more. That's a little confusing right now, but we'll have a visual representation of it that will show you how it's processed. But this is to just get you started in thinking of like, okay, there is a way where we, given a list of some type, what is a way that we can automatically go through it? So starting a little bit as like how this is represented, you'll have the overall graph, vertices and edges, where a graph is a component of vertices and edges, where vertices are a list of whatever you'd like, and the edges are going to be the actual relationships tied to each other. So thinking about like how this would be applicable in real life, there's two fairly common questions that are used to depict this, and they are the 7 bridges of Königsberg. Please correct me if you're actually familiar with that word. And the traveling salesman question. So the 7 bridges of Königsberg is a situation where there's 7 bridges in an area, and they want to know, is there a way where you can cross every bridge in the city at least once? And what is a way that you can do that in a way where if you just plug them in, what's the math equation? You can figure it out. The other instance is the traveling salesman. And this is the one that is a little bit more familiar because it's a little bit more common in today's workplace, where given X amount of locations with X amount of weight, in this instance, like certain values, whether it be traffic, hills, distance, what is the most efficient way to get to all of these places in a certain amount of time, but also be able to return back to where you came from. And this is something that I see a lot with just mailmen, where you got to hit X amount of houses, but you also have to return back to home base. You're trying to think of like, okay, the truck can hold this amount of gas, it can travel this many miles. What's the best way where they could calculate to hit all these places, but also make it back home? So for right now, I'm going to take a little bit of a deep breath because this is where we're going to jump in to the actual algorithms. So we're going to hit a woo-saw because the first one, it's relatively straightforward. We're going to go through the breadth first search, and this is what was mentioned earlier. And I know that the text to my right, your left, the pseudocode is going to be relatively tiny, but I think that the pseudocode is important just so you can get a better idea of how this would translate to a tech perspective. But from the breadth first search, what it does is it's starting from a given node, you go through one level at a time, and we'll sort of iterate through relatively calm way. And how this is done actually programmatically is you'll have a queue or a list in this instance. And what you'll do is with each object, you'll have a list where it's empty and a list of the actual numbers. And then you'll move the list from one where it's visited items and non-visited items. And so it'll go from 0, mark 0 is visited, go to 1, and then for all neighbors in that are directly part of it, put that in the list of visited. So in this instance, starts with 0, tracks 1, then 2, then 3 as visited, goes back to the top for what is not visited, starts with 1, then tracks 1 as visited, but then it sees what what children are attached to it, gets 4, gets 5, sees that it has nothing else, circles back up to 1, then goes to 2, and repeats the process. Any questions on that before we move on? Go ahead.
So is it the depth of how you're searching, or is it more to do with the calculation to get the search results?
It's the depth of your searching. So the kind of a way to think of it is it's sort of sequential. So in a mathematical perspective, this will be traced as, if you think of it in coordinates, it would be like if it was 0, would be the head node, or in a 3D array, it would be 0 at 0, 0, and then 1 would be at 0, 1, and then you could translate the first coordinate of that as the parent, and then the second one as the child. And what it's doing is it's iterating through the parent nodes, cataloging the children in a way so that it can actually just search. So this one is really, it's just looking for a thing. It's not organizing. It's not sorting, just searching through. And the numbers here are just to place how you can actually go through it. This could be an arbitrary list and it would still search through the same way without sorting it, without doing any form of sorting. Any other questions before we go to the next one? Cool. So depth first search, this one is a little bit more complicated because this one requires recursion. Recursion was about a month and a half for college for me, that I am narrowing down to a slide. And so this one, recursion, essentially is calling a function within a function. And a decent way to think about it is like in Rick and Morty, there was one episode where there was they were creating energy for a bigger, or actually we'll dial that back. If you think we're in a simulation or not. The simulation theory is one of great ways to explain recursion, because hypothetically, let's say that you are in this thing, you're running a simulation of life. So how do you know if you're doing that? You run a simulation of life. And in that simulation, they have the same question of like, are we in a simulation of life? So they're running a simulation. And that's how it'll keep going and going and going and going until you have a breakpoint where it stops and you get the answer as it goes all the way back up. So in this instance, using the same analogy, we'll have number 1 will be the real reality. And they will be asking, are we in the real world? So it'll go to 2, and 2 will either have yes or no. So in 2 also doesn't know the answer quite yet, so they go to 3, and then 3 goes to 4. And 4 responds saying, we might be in a reality, but we're going to assume no. So they go back up to 3, which goes back down to 5, which is like, yes, we are absolutely not here. And then it goes back up and it iterates through that same process of, once it has found whatever it's looking for at the furthest left node, meaning the furthest left possibility, it'll go back up and do the same type of calculation on the right side till it's done all of the nodes at that level, and then repeat the process. In the code, you'll see that it runs the DFS, which is depth first search, with the graph taking in a specific vertex. And within the while loop is when it's searching through all the things that have been visited and running in that similar process of just like, okay, have I visited this? If not, let me go to the right. Or if have I visited this, let me mark it as visited, and then do the action to go to the next node. All right. So this one is where the fun begins. This is the most popular one, but also the most terrifying one. Actually, no, the next one after this is the most terrifying one. Then it's all uphill after that. For this one, this is the most popular algorithm when it comes to graph theory, Dijkstra's algorithm. And this one is very important to remember that this only deals with positive numbers, but dialing that back a little bit further, this takes in non-negative weights as the edges, meaning like they have to be positive numbers to calculate the relationship. And how this works is giving a source and a destination or any type of objective. You have to think, okay, what is a way that I can calculate quantitatively the most efficient way to get to this point? And this is the first algorithm that actually does that. And one of the things that it does is you'll see like the handful of numbers, and for whatever path, each time that it goes through, it's going to calculate what the smallest number, aka the smallest weight or the smallest distance or most efficient to get to the objective, whatever that may be. In the pseudocode, it traces it to, for each vertex, it keeps track of the distance to a point, and then it stores it to find the smallest neighbor. So for each relationship, and we'll just start with the first one, vertex C1. It calculates, okay, if I'm trying to get to the end, which one is going to be the smallest value, 9 or 4? In this one, it's a little bit obvious because it's 4. But then it'll go to where it is the weight V3. It says, okay, well, 1 is smaller, 2 is pretty close, so I'm going to look at both of them. And it'll go through the whole process of saying, okay, 1 is smaller, I'll go there, between 4 and 8, which is smaller, 4, and then 2. So this is a one way where it calculates the smallest one. And the natural like follow-on question is like, okay, but how does it know that this is the smallest one in the entire graph? And what it does is it iterates through the entire graph as it's going through it. It doesn't just take the smallest one at each vertex. So it'll go through this. And one of the things that you'll notice is on the second line, it'll say the distance of V is infinity and the previous of V is undefined. So in this instance, infinity is an arbitrarily large number. So like 9999999. So at this point, it's constantly being like, okay, if this is the distance of the first one, if it's smaller than infinity, let's make this the new distance. And each progressively smaller one, it will add to that number, which makes things a bit easier in a sense. So what it'll do is if the distance for the first line, V2, V3, is 4 versus 9, it'll be like, okay, well, let me go back and we'll start with 9 and then we'll go to 7, and me checking, or it'll compare with the previous queue, saying if I'm at V4 and the value is 16, but the other one was 5, I'm just going to ignore you. We're just going to move on. And then it'll perform the same computation at each level. So at each time, it's checking all the ways that you could get there. And if it's the minimum value, then we're going to keep it and just keep going. And then at that, the key thing to remember about all this is that this only takes into account 1, positive numbers, and 2, bidirectional. So, well, unidirectional. So they're all going one way. Here is an example of how this actually plays through. And you'll see that it's taking in all of them, comparing all the weights at each node, and then adding to a continuous distance for each of them, and then storing that distance at the specific node-ish. But think of this as like an array where the weight of this one isn't actually 15. This is the weight of everything up to this point. And so this one, it finds that the overall weight here is 18, and that the path that it showed was the shortest path to get to that one. So this one, I have to admit, is terrifying. Like, this is one where I am struggling to this day. It's very similar to Dijkstra in terms of how it generally operates. But this one, the key factor that you have to take into account is that this one handles negative weights, which leads to an error called a negative cycle, where the best example that ChatGPT gave me especially after going premium, was a child running around a playground, getting caught on the merry-go-round and becoming exhausted before they can get back to their parent. To which I was like, okay, that's fine. That's what we're. It's already 1 o'clock. So the literal definition of what a negative cycle is when you have a section where there are the negative values sort of put the state of the graph in a perpetual decline, and I'll show it on the next slide. But the thing here is you have to be able to check for a situation where if you're going through the graph and there is a cycle where you can just go through that, and if you start at 15, but this cycle can constantly, if you're going through it, will knock you down to like 13 and 10 and et cetera, where it just runs it's completely out. It's a way where you can just your whole graph is basically worthless because it's giving you a false positive in terms of the shortest path. Okay, so the question was if you does it minimize the result for places you can revisit it? And yes, it does. This is an example of a negative graph, and it's sort of gets on what you spoke of, because it's you get into a point where you do have to go back to where you were. So the if the code doesn't check for it, you might accidentally, I guess, go back to the places where you already were. But you'll see here that if you're running through it and you're trying to get from, let's say, 1 to 7, you'll get stuck here where as you're going from 7 to 8, and let's say that the value at that point is 10, you'll get down to 8, or you'll get up to 10, then back down to 8, then back down to 6, when hypothetically, like, you could have just stopped here to begin with, and it's sort of like wasting time, and you don't have to go back to the same node. But this is where it gets tricky and where I'm kind of confused, because as you go back to where we were previously, the actual algorithm, what it's checking for is if the overall number of the weight is less than the distance that has already been traveled. And how this actually goes through it is it will go through the entire graph. It will have a number. And what it will do is it's sort of like this algorithm is just sort of the distance of the entire thing. This here does a separate iteration of you going through the graph. And if it goes through the iteration doing the exact same thing again, and it still has that negative value, it would decrease the distance. So hypothetically, me walking to just to that desk right over there, if it takes me 10 steps, but I go back somehow, and now it's 8 steps, and somehow it's 6 steps because my legs got really huge in a short period of time, it doesn't make any sense. And this is why, like, not the negative cycle is a important thing to detect, but also relatively hard. And how this does it, how I've seen algorithms where they just check for non-negative distances period, or negative distances period, where that doesn't make sense to me, because this is supposed to account for negative weights. And we're supposed to be able to have things where it could potentially become negative depending on how big that value is. But in practice, they are tracking the overall distance and making sure that the distance of it going through once is always the same distance from getting from A to B. But non-negative cycles will adjust the overall distance each time that you go through this iteration. And an example of how the program actually runs through these things. Here it's just looking for the shortest path from 1 through 6. The first path shows that it's proper 6, then 14, then the last one is 4. And the key thing here was just the negative values take away from what the overall distance might be. And so some actual uses of this is quite exciting, actually, because one of the things this is used for is in chemicals and measuring like chemical reactions. For example, if they're tracking heat loss or heat gain, or making sure that it's a certain temperature, That's one of the ways that it's also tracked. It's also relatively used for routing. Dijkstra's is used for, I believe, PGP routing, but don't. Oh, say again? OSPF. Thank you. Um, but this one is also used for being able to track if there's like degradation in the network, or this one just takes, this is the first algorithm that we have where it takes like life into account if there's any contingencies that might be happening. And then the next algorithm, I call it the YOLO algorithm, but it's the Floyd-Warshall algorithm. And this one is very similar to brute force, because what this does is it takes every node and it creates the distance to every other node in and it tracks it that way. So it'll be like, what's A to E, what's C to D, what's B to 3, what's the directions to my grandma's house. It'll grab all of them. This one's relatively simple because this one is just a couple of for loops as it's iterating through every single one and annotating every single one. And how this actually looks like is as it's going through, it'll be like, okay, what's A to this one, B to this one, tracking every single relationship and adding the weight to the overall graph. Any questions on this one before we go?
General question.
Yes.
What influences the weight? What sets the position being set? The number of hops that they have to take from node A to node C, or?
So it's relatively arbitrary. No, it depends on, in this specific instance, it's arbitrary, but the most common example that would pop up is like, we'll take GPS, for example. So what's the shortest distance from here to, let's say, the cafeteria? And we're going to measure that in steps that it takes to get around, or distance, or miles. And so the thing is that the numbers generally come from how you want to quantify the relationships between the objects.
So it's something that you have a degree of control over.
Correct.
Thank you.
No problem. So with this, there's a bunch of algorithms that are out there, but these were the most popular ones that I was able to find. And then after this, it sort of gets into a really, really deep math. Like, I saw a bunch of Greek letters that I just didn't have the eyes for at that point. But getting into more like how this deals with our day-to-day as like cybersecurity professionals or people working in computer science, there's a handful of tools that are out there where we can start to do like our own thing at this point. And so you'll see these are a handful of tools that are like used in tools very similar to like Bloodhound, where there's Python, which deals with Python, specifically the Network X module, which helps with graphing. Neo4j, which is sort of the backend for Bloodhound, and Cipher Query that's attached to it, which is the language that is used to parse the database, and how you can inject our own relationships between the objects. And you'll also see a couple of the other alternatives that you can use based off all that. So getting into more so off that, how is this like actually used? And the big buzzword for a lot of this right now is ontology. So ontology is basically like, it's frequently described as the nouns and verbs of business to inform decisions, which may be some mission statement somewhere, but it's formally defined as the representation of knowledge that sets out the concepts and relationships within a particular domain. Realistically, so how this is used in real life is, and we'll just use my sister, for example. She is a nurse, and she works over 100 people. The people in this instance would be the objects. There's time slots that need to be filled. There's patients that have certain needs. There are specialties that the nurses have. And they can just sort of be like, okay, if we have 100 nurses, some for NICU, some for emergency, and we have to have 50 of them in for this date, 10 of them in for this date, 30 of them for this date. What is a way that we could have this done in a way that works? And where can they be? And that's one of the things that could be used where they can be like, okay, we'll have, since this nurse works 10 miles away, it's easier to pull her in on a weekend. So we'll have her scheduled for this time, this time, this time, and this time. And then we'll have these ones come in for bigger emergencies. And it seems like relatively abstract in ways where like what we were just talking about, these algorithms translates to business decisions. But another way that I like to think about it is like, if we're thinking about how many chicken tenders Tyson can make in a day, and they have to take into account how much chickens they have to make, how much the chicken steroids are costing these days, and how many they have to push towards the grocery stores. All of those things can be tracked. All of those things can be studied, and you can add all of these things in a graph and hypothetically use that as a way to be like, okay, where is our funnel? Where are we having some issues? Where are some ways that we can make this a little bit better? But more so, how is this used in cybersecurity? Bloodhound trademark, TM, potentially, is one of the big ways that it's actually used. But in the instance of within cybersecurity, the how I was first formally defined what hacking was taking something, and it doesn't really matter what it is, but like using it in a way that it's not intended. So like one of the first hacks that I think a lot of people hear about is putting a dollar, like a tape on a dollar bill, putting it in a vending machine and pulling it out. So in that instance, the vending machine is supposed to be able to take cash. It's not supposed to let cash come back out, but the user can allow you to do certain things that way. Within cybersecurity, one of the things that Jared and Will Schroeder were talking about earlier today is how identity and the things a person can use that they're supposed to be able to do, how that can be aligned for some malicious intent, but it's hard to actually figure out what that is. But graphs help out a lot with that, because you'll have like a person who has X resource who can perform X actions. And you could do this by doing at least a terabyte worth of Excel documents and squirming through it that way, or plugging it into a graph and defining whatever your objective it is, whether it be like domain admin, owning a SQL server, and just seeing what relations have a path to that direction. Another instance that it can be used in that's relatively popular now is threat intelligence. And I believe this is a Threat Connect report. But this one was really interesting for me since I'm on the defensive side, because it's used to sort of, I know that threat intelligence has been a hot button issue because whether or not it's important or effective has always been a back and forth. But I feel like graphs are one of the best ways that you can actually show value for it in a way where it's relatively understandable. One of the key things that was very popular in the IC or the intelligence community is how can you describe that a threat has the capability and intent to target whatever you're looking at. And the capability and intent can be relatively easy to find by the object and the relationship to whatever you're looking for. So let's say like a specific APT has X domains that are tracked. They have a history of doing X actions, which are tracked. So you can have an object for the APT, an object for actions tied to hypothetically whatever targets have been hit previously, and see how many of these targets align with whatever you're working on. And potentially it could be one thing that's yours. And that's one of the ways where you can sort of build detections around what things might be looking your way. And that gets me into my next one, how it's used with like detecting malicious activity. And this one, it's the very blank slide, but I think it's really important to bring up. Just think about how graphs could be used in detecting things outside of what's here, because the most prominent one I found online was the anomaly detection, which is based on like if you have a known good of your environment, which is relatively common in general, just being able to figure out, okay, what's outside of that. That is what I would like. It's a relatively easy way to be able to find bad things. And I can't personally think of another ways that you could build detections off of this other than very similar to how I guess like Endgame, where they had a list of process trees or files that would all pop out from like one malicious thing. And it could be really helpful with like reverse engineering and detecting how what certain processes might be tied to certain actions, tied to things that have been known to have been bad previously. It's a really complex topic of just that. And that's why I imagine most people just stick to like, I know what good looks like, so I'm just going to find bad that's not good, versus I'm going to essentially develop my own thing and run it off that. But generally, in closing, I'd like to talk about there's a book. Let me get the name of it right, but it is it's not complex or it's not complicated. And it talks about the topic of complex versus complicated, where complex refers to a system of many intricate parts where the whole's the sum more than the sum of its parts, versus complicated is just something that is difficult or intricate. And I feel like graphs are a great way to make something complicated and not complex. Meaning, a good example for some things that are complex could be like raising a kid. Like that is one thing where you don't want to raise a little tyrant, but you also don't know how to do it. However, there's a bunch of books that are out there on how to raise kids, how to like do schooling, training them, all those things. Those things are complicated. They're hard. I can't get my niece to not eat like just these green goldfish to save my life. And if you're ever asking, like, where do you get green goldfish? You get the normal goldfish and you throw the rest of them away and just get the green ones. So it's one of those things where if you can figure out a way to take these complex things and then have some system put in place where it takes away a lot of the thinking or a lot of the hard work that you have to do so you can just focus on thinking. It's a way that you can enable decision making and enable just forward progress. And that's all I have for right now.
Thank you, Nicholas.